We'll discuss the laminar flow in pipes. So here, all we know the definitions of the laminar flow, and we know when the flow will be laminar. So especially, we decide by using the Reynolds number. You know when the Reynolds number is less than 2300. So when the Reynolds number is less than this value, we can say this is laminar, right? So today we're going to discuss what is the laminar flow in pipes. So the first assumption is that the flow is laminar, and we'll discuss this here. Our assumption it is a steady flow, laminar flow, and incompressible flow. And let's say this is the fully developed flow, and you all know fully developed meanings. So we discussed it earlier, right? So the aims here is, from this video we'll actually we'll obtain the momentum equations by applying the momentum balance to a differential fluid elements. Let's say this is the differential fluid elements. This is the cross-sectional view of the flow. You can see this is the fully developed flow. It's showing the parabolic shape, and you see all the notations here. So we will apply the momentum balance to a differential volume elements, and we'll obtain the velocity profile for a laminar flow, steady laminar flow, and the fully developed flow. So what is happening here? You see, look at this schematic. This is the pipe cross section. This is the pipe wall. The flow is going this way. This is the velocity profile. This is the center line, okay, where the velocity is maximum. You see, this is the maximum velocity here at this point. So this is the radius constant r, and this radius, this is actually the radius, which is the variable. Actually, it's changing with this streamline. So we took this very differential section here. So what we can say, when it is a fully developed flow, fully developed laminar flow, so this is the fluid particles are moving, okay, along these axial directions. So the velocity profile, it will define by ur, and it will be constant. So when the flow is fully developed, so if it is, let's say, another 10 meter long, so we will get a similar profile here, a similar fully developed profile here. So that means this ur, that means the profile, the velocity profile, it will remain unchanged with the directions of the flow, because we have no motions in these radial directions, and the velocity components, in the direction normal to the 5-axis, it is everywhere 0 here. So we can say this is a steady flow and the fully developed flow, and it's not changing anymore. So now we took very small section here, okay. This is a ring shaped differential volume. We put it here. So the only thing, when we took this dr, this is the radial, you can say the thickness, okay, and this is thickness, and this dx, this is the the differential length. So the only thing on this volume element is happening is the pressure and the viscous effects. So we must need to do some pressure and the viscous balance. So this is the the shear stress, and this is the pressure. So if this section, if the pressure is P, we said this is very differential section, this length is dx, so we said P x plus dx. When we're talking about this thickness from here to here, this is dr. So if the shear stress is here tr, we said at this section it is tr plus dr, okay. So that's actually the schematic you can see for this differential volume. So now what we will do, we'll do a force balance for this volume element, okay, in the flow direction. So you can see the flow directions here. All this arrow, it's showing the directions. So what we did, we just calculated the force, and you know how we get the force from the pressure. So we need to just multiply with the area here. Actually, I will not explain all these calculations in details, but I will just quickly go through it. So we got, you see, this is the pressure force this way, and this is the positive direction. So this is for, at this point, it's the negative direction. We said this is negative, then the tr, this is the shear stress, and you see it is in the opposite direction, so negative tr plus dr. So now if we actually divide 2 pi r dr into this all parts of this left hand side, you see right hand side is 0, and if we rearrange it, then we'll get it like this. Okay, so we'll get it like this. So now we have two numerators here, dp and d are tau. Okay, so what we can do, if we substitute the value tau equal negative mu dr du dr and divide by r, and taking if you also divide by r, then, and also if we take the mu, this mu, it is equal constant, so then we will get these expressions. If you go through the books, then you will see the detailed calculations over there, so we will get these expressions. So we have this quantity, you see, du and dr. This is actually the change of the velocity in the radial directions, du dr, rate of change of the the velocity in the radial directions. It is negative in pipe flow, and so negative sign indicates is negative sign. Actually we can write it down like this here. We can just write it down like this: du dr, this is equal negative du dy. So the coordinate system I showed you earlier. So y actually will define it as capital R minus small r. So we had the direction, it was, let's say u, it was y. Let's say it's something we discussed here. Yep. So now if we simplify this, let's say we had the previous expression, this, we need to integrate it just twice. If we integrate it 2 times with respect to for, well, u is the variable here, the velocity, we're looking for the velocity profile, so u, so we integrate that twice, so that means we'll get 2 constants, the c1 and c2. So it is a long calculations and it's not important for us, so I'm not showing it here. So here we change the boundary conditions. We solved a similar problem last week, so you can get it from there. Now once you will substitute all these values here, then the ur, it will be kind of like this. Okay, but once we have these expressions, so velocity profile, we know in fully developed case it is parabolic, so we will get the maximum velocity at the center line and the minimum zero velocity at the pi pole. So that means the velocity will be minimum, it should be 0 at the pi pole, and it should be maximum at the center line. Okay, so that we already know. So we should deal with the average velocity. You see, we actually, okay, we didn't show that on here. So as the velocity is 0 here, maximum here, so then how we will deal with these problems? So it's better to calculate the average velocity, something like this. So we already know the average velocity definitions, so if we apply that on, and we'll get it like this. The average velocity definition we know from previous slides, so this is the average velocity definition. So if we substitute the value ur here, and if we simplify this, actually after all the calculations, we'll get it is like this. And then dp dr, it is already, we know this value, you see we previously calculated this value here. So if we combine all these equations, okay, equation these equations, and if we combine previously we discussed the equation 8.2 from your book, so that means this is the average velocity equation. So then we'll get it ur equal to into average velocity 1 minus r squared plus r squared. So this is actually the final profile, the velocity profile for a fully developed and steady laminar flow. So here actually I was so for whatever I said, I actually need to do a lot of calculations, and it takes it will take like 30 to 40 minutes if actually I want to explain all these equations. But this is not important for us. We just need to know the final expressions of the the velocity profile. So this is the velocity profile where we used the the average velocity for this problem. But what do we know? The maximum velocity will be at the center line. So at these positions, if it is our coordinate system, look, this is the coordinate system x, this is r. So x means here, if this is r, so that means at that position, at this center line, r, this is equal 0. So if you actually want to get the maximum velocity, let's put this is equal 0. That means this term, it will be 0. So the u max, it will be 2 into the average velocity. So the maximum velocity for a fully developed laminar flow pipe, this is how we will calculate it like this. It is just 2 into the just average velocity. So that's actually how we will calculate the maximum velocity, and this is the velocity profile we need to use for some problems. So that's all you need for study laminar flow, and all this calculation, this is actually you don't need to know. And yeah, I just wanted to make the video short, so I didn't explain, and even I didn't expand it, because if I want to show you how to do this and how to change this, it will be so lengthy and a lot of calculations. So forget about that. You just need this and this, and we're going to use that on these two equations when we will solve